Hello everyone, my name is Pallavi Jaswal, college roll number 205006. Today I am going to explain a topic linear transformation and its properties. Starting with the basic introduction. The significance of vector space arises from the fact that we can pass from one vector space to another by means of functions that possess a certain property called linearity. Linear transformations are functions of vectors in one vector space V with values which are vectors in the same or another vector space W, which preserve linear combinations. The theory of linear transformations can be applied both to infinite dimensional vector spaces and to spaces of finite dimension. In the latter case, matrices are introduced to represent linear transformations. Many practical applications are found in the study of linear transformations of a vector space into itself. Now, the matrix representing a linear transformation of V into W depends on the choice of a basis in V and a basis in W. Whenever matrices are used to represent anything, the first problem is to see how a change in the choice of basis determines a corresponding change in the matrices representing linear transformation. The two matrices which represents the same linear transformation with respect to different set of bases must have some properties in common. This leads to the idea of equivalence relations among matrices. In this way, we greatly enlarge our understanding of the world of matrices from the viewpoint of transformations and for its own sake. Now coming to the main topic, linear transformation. Let V and W are two vector spaces over the same field F. Then a function t from V into W is said to be linear transformation or linear map from V into W if t of C alpha plus beta is equals to C t of alpha plus t of beta. For every alpha comma beta belongs to V and C belongs to F. If V is equals to F such that the linear transformation T tends to V is known as linear operator. The linear transformation T is also said to be vector space homomorphism over F or an F homomorphism. If it is 1-1, then it is known as monomorphism, and if it is onto, then it is known as epimorphism. So a vector space homomorphism over F is known as isomorphism if it is 1-1 and onto both. For a linear transformation T such that V tends to W, the set V is called the domain of T and the W, which the images of T are defined, is called the codomain of T. The linear transformation that maps every element of V onto the zero element of W is called zero mapping. The set of all the linear transformations from V of F into W of F is called the space, which is L V, W. Now we will understand the range or image of T. Let T such that V tends to W be a linear transformation. Then the image of T is defined as range of T is equals to beta belongs to W such that beta is equals to T of alpha and alpha belongs to V. It is denoted by image of T, which is written as IMT, or range of T, RT. Properties of linear transformation. Let V of f and W of f are two vector spaces and T be a linear transformation from V to W, then it possesses four properties. The first one is transformation of 0 is equals to 0 dash, where 0 belongs to V and 0 dash belongs to W. Transformation of minus alpha is equals to minus T of alpha for every alpha belongs to V. T of alpha minus beta is equals to T of alpha minus T of beta for every alpha comma beta belongs to V. The last property is T of summation n to I is equals to 1 Ci alpha I, which is equals to summation of I is equals to 1 to n Ci transformation of alpha I for every alpha I dash s belongs to V and Ci dash s belongs to F. Now starting with the first proof. The first theorem was T of 0 is equals to 0 dash, where 0 belongs to V and 0 dash belongs to W. So let alpha belongs to V. It means that transformation of alpha belongs to W. So 0 belongs to V. Now transformation of alpha also belongs to W, which means transformation of alpha plus 0 dash is equals to transformation of alpha, which can further be written as transformation of alpha plus 0 dash is equals to transformation of alpha plus 0. Here we did at the place of alpha we write alpha plus 0, which again come as alpha. Now transformation of alpha plus 0 dash is equals to transformation of alpha plus transformation of 0, and by the left cancellation law we can prove that 0 dash is equals to transformation of 0. Here our first theorem is proved. Now here is the second formula. It is transformation of minus alpha is equals to minus T of alpha for every alpha belongs to V. V is vector space. Let alpha belongs to V, then transformation of minus alpha can be written as transformation of minus 1 into alpha. We can take out the minus 1, which will be written as minus 1 transformation of alpha. Now as a 1 is not considered, so it will be minus T of alpha. Now our second formula is also proved. Coming to the third formula. The third formula is T of alpha minus beta is equals to T of alpha minus T of beta for every alpha comma beta belongs to V vector space. We can write T of alpha minus beta as T of alpha plus in the bracket minus beta, where alpha comma beta belongs to V. T of alpha, now separating the transformation we get T of alpha plus T of minus beta. Using the second formula, as we have showed earlier that T of minus alpha is equals to minus T of alpha, here we see that there is T of minus beta, so we can write it as minus T of beta. Now the equation becomes T of alpha plus in the bracket minus T of beta. So plus minus is minus. Now we have proved the following formula. T of alpha minus beta is equals to T alpha minus T beta. Now proving our last formula. Transformation of summation I is equals to 1 to n Ci alpha I is equals to summation of I is equals to 1 to n Ci transformation of alpha I for every alpha I dash s belongs to V and Ci dash s belongs to F. So transformation of summation I is equals to 1 to n Ci alpha I can be written as transformation of C1 alpha 1 plus C2 alpha 2 plus to the Cn alpha n. The result is provided by induction formula. Let transformation of summation I is equals to 1 to m Ci alpha I is equals to summation of I is equals to 1 m Ci transformation of alpha I. Let it be equation 1. So for m plus 1 we have transformation of C1 alpha 1 plus dot 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 plus Cm alpha m plus Cm plus 1 alpha m plus 1, which can be which is equal to transformation of C1 alpha 1 to Cm alpha m plus Cm plus 1 alpha m plus 1. Now we can write it as transformation of summation of I is equals to 1 to m Ci alpha I plus Cm plus 1 alpha m plus 1. This equation can be written as summation of I is equals to 1 to m Ci T of alpha I plus Cm plus 1 T of alpha m plus 1. The current equation came out from the formula second. Now the above formula second line can be written as summation of I is equals to 1 to m Ci T alpha I. Let it be equation 2. For m is equals to 0, transformation of C1 alpha 1 is equals to C1 transformation of alpha 1. Here C is constant, so it happens C1 T alpha 1. Let it be equation 3. Then we can conclude from the result second and third. We can say that the result is true for all n. It means transformation of summation of I is equals to 1 and Ci alpha is equals to summation of I is equals to 1 to n Ci T of alpha I. Now our last formula is also proved. Now we will see an example of linear transformation. Here the question is explain whether the transformation T such that r square tends to r cube. The question is T of x comma y is equals to x plus 1 2y comma x plus y is linear or not. Here we have to show that the given function is linear or not. We will show it by, as I will tell you. Now the solution is we have r square tends to r cube be a transformation. Let alpha is equals to a1 comma a2 and beta is equals to b1 comma b2. These both values belongs to r square, and let be any constant c which belongs to r. Then transformation of c of alpha plus beta can be written as transformation of c of a1 comma a2 plus b1 comma b2. Just put the values of alpha and beta, alpha value a1 a2 and beta value b1 b2. We will get this equation. Now transformation of opening the bracket, we get transformation of ca1 plus b1 comma ca2 plus b2. Now collect the coefficients. ca1 plus b1 plus 1, 2ca2 plus 2b2 and ca1 plus b1 plus ca2 plus b2. Now taking out the common c here from the c multiplied coefficients, so it will be c common a1 comma 2 a2 comma a1 plus a2. The remaining will be b1 plus 1 comma 2b2 comma b1 plus b2. Here the formula we know that c t of alpha plus t of beta is equals to c t of a1 comma a2 plus t of b1 comma b2. The c it now see that it can be written as c a1 plus 1 comma 2 a2 comma a1 plus a2. In the second bracket it will be b1 plus 1 comma 2 b2 comma b1 plus b2. From this relation we can see that t c of alpha plus beta is not equals to c t of alpha plus t of beta. So the function given t such that r square to r cube defined by t of x comma y x plus 1 comma 2y comma x plus y is not a linear transformation. Thank you for listening my presentation.